This is PreCalc 12, Chapter 4.4. We will be determining the restrictions on composite functions. We will also be determining composite functions in reverse. Determining the restrictions is very different from the restrictions on combining functions, and it is far more difficult. Recall that for combining functions, we just take the most restrictive domain. This is not the case with composite functions. Let's look at an example. The domain of f is x is greater than or equal to 0, and the range of f is y is greater than or equal to 0. For x squared plus 2, we have the domain is all reals, and the range, this is a quadratic, and it is already in vertex form. Therefore, we can simply look at the minimum value. The vertex is the minimum value. So this is y is greater than 2. Let's look at the explicit equation for f of g of x. And that is the square root of x squared plus 2. To determine the domain of f of g, we look at g first. The domain is all reals. The range is y is greater than or equal to 2. Now remember, this output is the input to f. Since y is greater than 2 fulfills x is greater than 0, there are no restrictions on the domain. So the domain is all reals. The range of f of g, again, we look at what's coming out of g and putting into f. Since our minimum value is 2, we want to put this as an input into f. And f is just the square root of x. So the range is y is greater than or equal to the square root of 2. Because 2 is going in, and we're taking the square root of that. Let's look at g of f of x. That equals the square root of x, all squared, plus 2. We can simplify this to x plus 2. Now let's look at the domain of g of f. Now we're looking at f first. Its domain is greater than or equal to 0. Its range is greater than or equal to 0. Since we're starting off with this, our domain must be greater than or equal to 0. Let's look at the range. Everything coming out of f is going to be greater than or equal to 0. So the minimum point is 0. 0 plus 2 is 2. And everything else is going to be bigger. So y is greater than or equal to 2. Even though this function is a line and takes all reals as input, we've already restricted ourselves because of the input from here. And these two expressions are equivalent but not equal. This expression clearly has a domain of x is greater than or equal to 0, while this does not. So your choice, you can reason it out explicitly, or you can find an explicit function for the composition and try to figure out the domain and range. As I said before, there are two types of questions. We can determine an explicit equation for a composition, or we can determine the possible equations to create the compositions. This is working in reverse, and this task is more difficult than determining an explicit equation. Let's look at a simple example. Determine the possible equations for the composite function h of x, square root of x squared minus 3. We need to find f and g. we'll let g equal x squared minus 3. Then f of x is simply square root x. So h of x equals f of g of x. What happens if we have a more complicated expression? What strategies can we use? We can use bed mass, and whatever steps we take for an evaluations are going to be good candidates for our inner functions. For polynomials, we might run into multiple uses of a variable, so completing a square is a way to get us down to a single variable, and then this will give us an inner function. Remember, combining functions is not composition. So let's look at an example. K of x equals the square root of x squared minus 4x plus 7. We start by completing the square. This is x squared minus 4x plus 4 minus 4 plus 7. We get x minus 2 squared plus 3. Now, we just pick any random number. I'm picking 4. And this number is just to help us evaluate using the rules of bed mass, and that will help us determine our inner functions. So we have 4 minus 2. And we just take little steps. Since we subtracted 2, our function is x minus 2. On our next step, it's 2 squared plus 3. So we take whatever result we get, that's 2, and then we're squaring it. So h of x must be x squared. The next little step is we take the result, that's 4, and we're adding 3. So our function is x plus 3. Finally, we're taking the square root of the result, so that's square root 7, and f of x is simply square root x. And k of x equals, and we do it in reverse order, f of g of h of j of x is our composite function. Let's look at a more complicated example. We're trying to find f, g, h, j, and k to create a composite function. So first step, complete the square. We have to pull out a first, which is 3. So this is x squared plus 2x minus 15. Now we complete the square by adding 1. This 1 is multiplied by 3, so we need to subtract 3 to keep the equation balanced. And this simplifies to 1 over 3x plus 1 squared minus 18. Again, we want to just pick a random number. Usually a number that doesn't result in 0 is going to be more interesting to work with. So our first step is 2 plus 1. This means our k of x equals x plus 1. Next step. We take the result, and the next operation we do is squaring. So this is 3 squared. Therefore, j of x equals x squared. Our next step we take the result, and the next operation we do is multiply by 3. So this is 3 times 9. And h of x equals 3x. Our next step, take the result, subtract 18. So, g of x equals x minus 18. And finally, our last operation is to do 1 divided by our result. So, f of x equals 1 over x. M of x equals f of g of h of j of k of x. There is one last example to cover. This one we can't use the rules of bed mass, and we have to do it by inspection, and we do it by looking for patterns. And the pattern that I see is this. So we are looking for F and G. So this is our innermost function. So we'll make that G. And then if we substitute that in, f of x is going to be x cubed plus x squared plus 7. And that completes this lesson.